Do we have any questions on homework for stoichiometry, or do you want to go over an example problem? How you feeling? Yeah, of stoichiometry? All right. I can pull it out of my head, or I can look back. You know, pull it out of my head? Or the other end, I don't know. Okay. So let's say we have sodium and water, and it makes sodium hydroxide and hydrogen gas. Okay. Let's say we have 2 grams of sodium that we throw in water, and we want to know how much hydrogen gas, how many grams of hydrogen gas this will form. This should form if everything goes perfectly, right? Okay, what's the first step? Balance the equation. You have to have a balanced equation from here on out, ladies and gents. You just have to. If it's not balanced, then you're wasting your time, okay? So, is this one already balanced? No, it's not. Okay, so we got 2 hydrogens, so this is always going to be 2. This is odd, sorry, this is always going to be even. This is odd, even. So let's make this even, right? So we have 4 here, so we better put a 2 right there to make 4 hydrogens there. You following? 2 oxygens, 2 oxygens, 2 sodiums, 2 sodiums, done. Okay, so it's balanced. Any questions on balancing? Would you rather me show my work? Is that how, I don't know, what helps, guys? Do you like me to do this and say, okay, we have sodium and all this? Would you like that better? Should I redo it?
I always do it. I always split it because it's like you're treating the OH as its own.
No, I'm not.
So you're treating
So I'm asking.
Oh, there's 3 hydrogens. I'm
No,
sorry.
no, you're good. Do you want me to show my work with each element?
It is helpful to follow along.
Okay, yeah, let's do it again. Okay, I'm gonna start here. Okay, so we have sodium, hydrogen, and oxygen. All right. So where's a good place to start? Well, if we look at sodium, it's balanced. Oxygen's balanced. Looks like we have to start at hydrogen. You see that? So let's start at hydrogen. We have 2 on the left, and we have 3 on the right. So it's not balanced. So we got to look at, this is always going to be even. This is odd right now, and this is even. So on the left is always going to be even. So let's make this one even. How do we do that? We put a 2 right there. You follow that? Okay, so now let's count. We have 2 hydrogens, that's 4 on the right. We have 2 here, so we better put a 2 there to have 4 on the left. We okay so far? Okay. And then we can count the oxygens next. We have 2 oxygens here. We have 2 oxygens there. Now the sodiums, we have 2 here, and we only have 1 here, so we better put a 2 right there. Follow? All right. Now I'm going to erase my work so I can do stoichiometry. Is that okay? Unless you have any questions. All right, so, whoops. I'm going to start with 2 grams of sodium because that's what I know I have. And I'm looking for how many grams of hydrogen gas. So So what can I convert to? If we look at our mole roadmap, if I have mass or grams of anything, where's the only place I can go? Straight to moles. Do you know what mole roadmap I'm talking about, guys? It's on your reference sheet that you get. It's right here. Okay, y'all have that in front of you to where you can look at? So it says grams of A, and the only place we can go is to moles of A. Okay, so we have grams of sodium, we're gonna convert to moles of sodium using, and it tells right here in between these arrows, the molar mass. The molar mass of sodium is it 23?
22.99.
Yeah, so basically 23, and you don't have to round. If you'd rather not round and get the exact what it is on the test, that's maybe worthwhile, okay? So 22.99, do you want to just do 22.99? Okay, 22.99, is that what it is, 99? Okay. Grams of sodium for 1 mole of sodium. Any questions so far? Okay, that goes away. We're not at grams of hydrogen yet, so we keep going. Now, if we look on our mole roadmap, we're at moles of A. We can either go to particles of A or moles of B. What do we want to go? We want to go to a different substance, right? So we're going to go to moles of B. Does that make sense? We want to go to, so A is substance 1 and B is substance 2. So we're starting at sodium and we want to go to hydrogen. So we're going from one substance to a different substance. So that means we want moles of sodium on bottom so they can cancel, and moles of hydrogen, because that's what we're looking for, on top. And what's the mole-to-mole ratio?
1, 2.
Yeah, 1, because that's the coefficient of hydrogen, and 2, because that's the coefficient of nitrogen. Y'all with me? Okay. So moles of sodium go away. We're at moles of hydrogen. We still have to go to grams of hydrogen, so keep going. And if we look, we're at moles of B. That's our moles of hydrogen in our example. We can go to grams of B, or grams of hydrogen. So we're going to use the molar mass of hydrogen. What is the molar mass of hydrogen?
1.008.
Close. Look at the hydrogen in our balanced equation. It's H2, so yeah, we have to multiply by, that's a common mistake. I've even made that during class one time. It happens. You got to be careful, okay? So we have, for every 1 mole of hydrogen gas, 2 grams of H2. And if we want to not round it, it's 2.002 or something, 02 or something. Okay. Anyway. So moles of H2 go away. And we're at grams of H2, that's what we're looking for, so that tells us we can stop. Are you following me? Okay. So you go 2 divided by 22.99 divided by 2 multiplied 2. Can we just cancel some of these 2's out? Can we do that? Yes? Yeah. Right? It's just a fraction. 2 divided by 2 is 1, so we don't need to worry about that. So 2 divided by about 23 is something. 0.0866 or 87 grams of H2. Not very much. Just enough to make an explosion, right? We good? But actually, that is kind of a lot, isn't it? Because it's grams, because hydrogen doesn't have a lot of mass. It's 1 gram per mole, so that's, well, anyway. We good? Yeah, question?
Sorry, there was just, you said because the coefficient of nitrogen.
Oh, did I say nitrogen?
Yeah, you said, okay. I was
Sodium, yeah,
like, oh, no,
my
that's
bad,
not
my
in
bad.
there. Okay.
Yeah, thanks.
No worries, okay.
I do that a lot, because there's a big N there, so it's nitrogen. Okay, my bad. So yeah, that's 2 moles of sodium to 1 mole of hydrogen. Thank you.
Thank you.
Yeah. I have a habit of just going too quickly, and then I'm going faster than my brain can think, so yeah, go ahead. Please stop me.
I have a question from
Yeah.
the homework. So it's calculate the moles of chlorine.
Chlorine gas,
Yep,
Cl2?
no, chlorine, Cl,
Okay.
and 3.61 times 10 to the 24th units of magnesium chloride,
3.61 times what?
10 to the 24th. Formula units of magnesium chloride.
So it wants to know how many moles of chlorine, yeah? Okay, good. So if we have one molecule of this, can we figure out how many moles we have? This is a representative particle, so, well, let's just start how we do all problems, right? Let's just start with what we know. We know this. Is that right? So it's 3.61 times 10 to the 24 formula units. Remember, that's just a particle of an ionic compound. We says we can use molecules if you want, but okay. That's the actual name for it. Of magnesium chloride. And I'm not swearing at you, I promise. Okay. So what's our conversion factor? What are we going to convert to? What does our mole roadmap say? Where are we on our map? Particles of A, right? And so the only place we can go is to moles of A. Do y'all follow that? Questions? Okay. And what's the conversion? Avogadro's number, right? 6.022 times 10 to the 23 formula units of magnesium chloride to every 1 mole of magnesium chloride. You following? So now, whoops. Formula units of magnesium chloride go away. Oh, good, that's a mouthful. And now we can convert moles of magnesium chloride into, can we go straight to moles of chlorine? We don't have a balanced equation, do we? If we have MgCl2, do you remember last time we talked about this? We can say this is 1 mole of magnesium for every 2 moles of chlorine. We can also say 1 atom of magnesium to 2 atoms of chlorine, right? But we converted it and it's the same thing. Do you remember doing that? Or should I do it again? You tell me. Do it again? Okay. So we can just call this, let's change this to, this means we have 1 atom of magnesium to every 2 atoms of chlorine, right? That's what that means. So let's convert 1 atom of magnesium into moles of magnesium. Can we do that? Well, atoms 6.022 times 10 to the 23 atoms of magnesium to 1 mole of magnesium. Are we good? Well, we can get an answer, but I'm not going to get an answer. I just want to show you something. Let's, down at the bottom, now let's change 2 atoms of chlorine. You with me? And we do the same thing. 1 mole of chlorine has 6.022 times 10 to the 23 atoms of chlorine. Following so far? Okay, so that goes away. Now, let's do this. 1 atom to 2 atoms is a 1 to 2 ratio, right? But now we don't have atoms. We have moles of magnesium to moles of chlorine. Do you see that this cancels with this? So what's the ratio of moles of magnesium to moles of chlorine? It's still 1 to 2. You follow? So even though we don't have a balanced equation, we can still say for every one of these, 1 mole of magnesium chloride, we have 2 moles of chlorine. Does that make sense? So we don't have to convert that ever again, if that makes sense in our mind. We'll just know that we can treat that as atoms, particles, or we can treat it as moles. It's the same. Same ratio anyway. So moles of magnesium chloride go away and we're left with moles of chlorine. So now we use our calculator and do 6.31 times 10 to the 24, divide 6.022 times 10 to the 23, multiply 2. And that's it. When I say that's it, I'm not saying that's easy, I'm just saying that's it. How are you feeling on that? Okay. We good? All right. Any other questions before we move on to today's topic? Okay, so we're finished with chapter 5 and 6, and now we're doing chapter 7 today and next time. And then we'll have an exam on Tuesday. Good, so we have today and next time to finish chapter 7 and maybe do a review. And then on Tuesday, we'll take the exam. Good? So it's in class on Tuesday, not Monday, even if the Canvas says it's on Monday, right? Okay. All right, today we're talking about thermodynamics or thermal chemistry. What does thermal mean? What? Heat. Okay, so we're talking about really what happens during a chemical reaction and what determines the rate of reaction, and anyway, it kind of helps us to understand what's going on a little bit better. So let's first of all talk about different types of energy that we deal with. You guys know what potential energy is? Potential energy, maybe I'll write it out. Just like when mom says, oh my gosh, she has so much potential, right? Well, he's not doing it right now, but he could, right? So it's stored energy. Okay. Uh-oh. And so if we have chemical, so we have H2O, for example. Do we have stored energy in water? Yeah, it's bonded together. We could break those bonds and get some energy out of it, right? Or maybe it takes energy to do it, one way or the other, right? Okay. And the other type of energy is kinetic energy. What's kinetic energy? Anybody know that? And this is not on the exam. I'm not going to, this is physics, right? So what'd you say, Andrew?
Like gravity, something on top of the hill,
Okay, yeah.
going down.
It starts to move, right? So we get in a roller coaster, we tick, what are we building? Potential energy, right? And then we go down and it converts into energy of motion or kinetic energy. Good? And kinetic energy is directly related to heat. Things are moving, they collide into each other. If they're moving faster, they collide more often, and you get more heat. Does that make sense? So kinetic energy is directly related to a change in temperature. You guys know what that triangle symbol means? Change in, how much it changes by. Good? All right. So let's, any questions about those two? So conservation of energy means you can't create energy, you can't destroy it, yeah? So that's the first, yeah, so that's the first law of thermodynamics, is you can't create energy, you can't destroy energy. And so it's just transfer from one form to another, okay? Or one object to another object, okay? So let's talk about enthalpy next. So this is really what you need to know, okay? That's just background. Enthalpy is the amount of heat released or absorbed during a chemical reaction. And the symbol we use, there's an H in the word enthalpy. So we're going to just say it's delta H. Well, it really stands for heat, right? Because I'm going to give you another word. It kind of sounds like enthalpy. It's called entropy. Just so you don't get them mixed up, right? So enthalpy has an H in it, so it's delta H. And what does delta mean? A change in, right? So we are changing the amount of heat. We might start with not a lot of heat, and then we might gain heat during the reaction, or we might lose heat. But either way, we're changing the amount of heat we have. Good? All right, so we have a negative delta H, and we also have a positive delta H. Negative delta H is when we release or absorb. What do you think? What makes most sense? Release, because we're losing it, right? We're losing the heat, and so it's a negative change. Does that make sense? So this is a release of heat. And we also call this exothermic or endothermic? Exo, exiting, right? Okay, and then positive delta H is an absorption of energy, or of heat. And this is endothermic. We good with those definitions? Okay. I think this one's the most straightforward out of all the ones we're doing today, but okay, so let's do some simple examples.
Question.
Yeah,
On the kinetic energy, it's related to what, with the temperature, releasing temperature?
change in temperature. right? So in other words, if it has a greater temperature, then it's going to have a greater kinetic energy, right? Lower temperature, lower kinetic energy. Okay? All right, so let's say we have liquid water, and we're turning this liquid water into ice or solid water. I know this isn't a chemical reaction, it's not a chemical change, but I'm just trying to start something simple so that we understand this idea. So is heat leaving the system or entering the system for this process to happen? What? Leaving? Yeah, it leaves, so you have water, and you take out the heat, and it gets cold, right? So this is exothermic, or negative delta H. That makes sense to everybody? And what if we do liquid water going to gaseous water? Where's the heat going? Inside. We have to take the heat. We have to put the heat inside the water so it evaporates and turns into steam, right? Or into gaseous water. So this is endothermic or positive delta H. Are we okay with that? Okay, now on the worksheet that you picked up, there's 4 more situations. Let's just kind of quickly go through those. So, snow forming in the clouds. It could be in the clouds or out of the clouds, and it's still what? Exothermic, right? Exothermic or a negative delta H, right? And maybe write both of them so that we can practice saying, okay, exo is negative delta H, right? Okay, burning a candle. Every degree endothermic? So listen, we gotta, and this sometimes is a little bit tricky, we gotta think about where the heat is going. If we're burning a candle, is that the same as melting the wax? Different, right? If we're melting the wax, we might be taking the heat in, right? And that's endothermic. But when we're burning the wick that's sticking out of the candle, that's really the candle, right? And we put our hand on the outside, what's happening? Heat is going out. Does that make sense? So sometimes we misinterpret what it's saying, or we're just not paying attention where that heat is going. Good? So that's but great thinking. Good? So that is also exothermic, negative delta H. We okay with that? Okay. So what about baking bread? Why do you say endo?
Cooking, like.
Yeah, to cook it, that's why you put it in the oven so that it can take in the heat, right? If you open the oven, that heat comes out, but that's not cooking bread, right? So, but baking bread is endothermic. Good. Does that make sense to everybody? So positive delta H. And then water condensing on a cold drink. Are we good with endothermic? So we have our drink right here, and we have little water droplets on the outside, right? Where did those water droplets come from? the outside, right? So the gaseous water in the atmosphere. And so it's really gaseous water going into liquid water. Is that right? So what are we doing? Getting rid of the heat. Does that make sense? So if you break it down and find out where that heat is going, it kind of makes sense, yeah? But if you just think about, okay, this is condensing, it's cold, so it must be, I don't know, right? You might think the other way. So you got to consider where that heat is and where is it going. So we got heat here and less heat here. Right? So it's going out. We're getting rid of the heat, and that's why it's turning into liquid. So this is endothermic. Questions? Or, oh my gosh. Did I say? Not endo. It's going out. I just said it's going out. It's exothermic. My bad. I'm just trying to make sure you're with me. Okay. Sorry about that. I wasn't with me. We good? Okay. Let's kind of mix what we're learning today with exothermic and endothermic into stoichiometry, because that's really where we're going to use it, yeah? Okay, so let's say we have two H2 plus O2 gives us 2H2O. And we have a delta H that is equal to negative 572 kilojoules of heat. Is that exothermic or endothermic reaction? Why is it exothermic, Albert? Because it's a negative delta H. You with me, guys? Okay. So since it's exothermic, does that mean heat is our product or our reactant? Go ahead, question.
You're saying it's a negative one because the numbers.
Yeah, yep, that's right. And if it was a positive, then it would be endothermic. Good? So if heat is exiting the system, do we say heat is our product or heat is our reactant? Our product. It's what we get after the reaction, right? So another way to write this same thing is 2H2 plus O2 gives us 2H2O plus 572 kilojoules. Now, why did I write plus and not minus? Because it's a product. When we write a chemical equation, it's always going to be separated by positives, by plus signs. You with me? If you want to subtract it, if it's endothermic, where do we put this? On the reactants. Because it needs the energy to react. Do you follow? Okay, now let's do an example. If we have 48.1 grams of hydrogen gas that burn, we want to know how much heat is released. So, ladies and gentlemen, what do we call a balanced equation again? A recipe. This is just a recipe. You guys ever make cookies? Do you ever change the amount of cookies you want to make? Yeah, all the time, right? Oh, this says it makes 12 cookies. Who wants 12 cookies? Come on, right? So you're going to double the batch. Or maybe it's just I'm trying to go on a diet, I'll just cut it in half, or whatever, right? We all know this, right? So we're not starting with 2 moles of hydrogen. We're starting with 48.1 grams of hydrogen. We don't know how much that is, but we don't have to know either, right? So we're just adjusting our recipe for what we have. That's all we're doing. That's all stoichiometry is. Good? So let's start with, I should have said that before last class, but okay. And maybe it makes things worse, I don't know. We're going to start with what we have, 48.1 grams of H2. And we're looking for the amount of heat. So if we look at our mole roadmap, what can we convert to if we have grams of something? To moles of that same thing, right? That's something we can do. So the molar mass of hydrogen is 2. Yeah, about 2 because there's 2 of them, right? So 2 grams of H2 to 1 mole of H2. Grams go away. We're left with moles, but we don't want moles. How do we go to heat? Well, this says for every 2 moles of H2, we have 1 mole of O2, right? And for every 2 moles of H2, we have 2 moles of H2O. It also says for every 2 moles of H2, we have 572 kilojoules of heat released. Does that make sense? It's just questions. Because if we burn 2 moles of hydrogen gas, it releases 572 kilojoules of heat. Okay? So our ratio is 2 moles for every 572. So we can use that in our conversion. 2 moles of H2, so the H2 cancels out, right? Moles of H2, to every 572 kilojoules of heat. So that's not on our mole roadmap, but do you see how does that make sense to everybody? What's up?
It just doesn't track to me. Like I think I get it, but I don't understand
All right, so let me say it in a little different words here. So these are our products, right? When we make cookies, it calls for 2 cups of flour and 3 eggs and how much sugar, right? Or whatever. If we use all of the reactants, all of the ingredients, all of the, whatever the recipe calls, it's going to make 12 cookies. You following? So that's our product is 12 cookies. Well, in this case, our product is 2 moles of water and 572 kilojoules of heat. That is the product when we react 2 moles of H2 to 1 mole of O2.
But where does the O2 come into play?
We don't use it in this problem because we don't care about O2.
Because we're only burning the H2.
Yeah. In oxygen, it's reacting with the oxygen. So we could figure out how much oxygen we need. We could. But that's not the question, so who cares? Right? So for every 2 moles of H2, we release 572 kilojoules of heat. Make sense?
Yeah, just because what the question is calling for essentially tells us to ignore the opposite.
That's right. And we could figure it out, and we could figure out how much water we make too, but we don't care in this particular problem. And remember, what we're finding is the theoretical, right? This is all theory. This is a prediction. That's all it is. I mean, when I say that's all it is, it's a pretty good prediction. unless you're not a very good, you don't make great measurements, then you're going to be off, right? So it's just to make predictions so that you don't have too much waste. That's all it is. Okay? And when we do this, we have 78 kilojoules. Is that right? Yeah? Okay. So that's how much heat is released.
So that becomes our delta H.
Yeah, that's right. And it's if we're to write delta H, now this, we could say this much heat released, or we could say delta H is negative 6878 kilojoules.
So that's when we remembered to throw the negative back in, because it's,
And so, yeah, we know it's released, so we know it's exothermic, right? And so if the test says the answer is, or if it asks how much heat is released, then we don't care about this, do we? That's our answer. That's how much heat is released. We don't say a negative heat is released, because that doesn't make any sense, right? But if it says, what is the delta H, then we would say negative 6878 kilojoules. That tells us it's released. Does that make sense? Do you want one more of those? Okay. So let's flip-flop this equation. So if instead I have water and I take in the energy, in this case I might, I give it energy so that I can split the water into hydrogen and oxygen. Can I just flip this equation and leave everything the same way? So in other words, can I do this? 572 kilojoules of heat plus 2 H2Os gives us 2 H2s and O2. Is this true? Yeah, now it's endothermic, right? If we're going the other way, it's endothermic. So we have heat on the left side, on the reactant side. We have to add that heat to the water so that we can split it. Well, it's probably more likely going to be electricity, but okay. Energy, whatever it is. Not kilograms. I said kilograms. That should be kilojoules, sorry. All right, so now let's say we want to produce 2 liters of hydrogen gas. How much energy is required? How much energy is absorbed to produce 2 liters of hydrogen gas? Are we good? Or maybe I should say how much heat is absorbed. Where do I start?
2 liters of.
Uh-oh, I have to give you more information, don't I?
There's no volume.
Yeah, I need the density of hydrogen gas is 1.293 grams per liter. Yeah, you have to know that. Otherwise, we're stuck. We know what we know, and we know what we're looking for. Where do we start next? We have a balanced equation, so where do we start next? with what we know. We know 2 bits of information. Which one should we start with? The answer is it doesn't matter. So where do you want to start?
1.292.
Okay, sure. 1.293 grams per liter. So that's a ratio, right? That's 1.293 grams for 1 liter. We could also write it as 1 liter over 1.293 grams. Which one should we use? Is that messing with you? Then here's how I do it. I start with the most simplest one. It doesn't matter, but here's another way to think about it. If you want to start with the ratio, we are looking for liters. Then, hold on. Yeah, I don't know. That's why I like to start with the most simplest. We have 1 unit versus 2 units. Let's do 1 unit. That easy enough? But again, you can try it, and if you got it flip-flopped, then what do? Just flip everything and you're good, right? But anyway, I'm going to start with 2 liters. 2 liters of H2. And I want to convert this to kilojoules of heat. Okay, I use this one. I'm not going to use that one anymore. Do I want liters in my answer? No, so where does it go? On the bottom. Liters of H2. And what can I convert to? I could convert to milliliters. I can convert straight to grams. Why is grams good? Because then we can convert to moles, and then, do you follow? Okay. So use what we know. If you can't, then we're going to have to convert to milliliters or something like that, right? So we still have this, and we can that has liters in it. So we're going to go 1 liter is the same as 1.293 grams of H2. So liters of H2 go away. Now let's convert grams into, using our mole roadmap, we can convert it to what? Moles. So 2 grams of H2, we just did this one, to 1 mole of H2. That goes away. And I'm going to erase this so that I have room. And I'm looking for what? Kilojoules of heat, right? So what's the ratio of moles of hydrogen to kilojoules of heat? What?
572.
Yeah, 572 goes on top or bottom. Maybe we don't know. So what unit do we have right now? Moles of H2. Do we want moles of H2 in our answer? No, so where does it go? On the bottom, so it cancels, right?
What, the 572?
Well, no, this is 2 moles of H2. Oh, yeah, you mean per 5, yeah. 572 kilojoules on top. Are we good? Do you feel pretty confident on how you know what goes where? Or are you still scared about that?
It's clear.
Okay.
Mud.
Uh-oh. So moles of H2 go away, and we're left with kilojoules of heat, so that tells us we can stop. And we should get 300 and something, around 66 of heat absorbed. Right? Questions? If you round it different, you might get a slightly different answer, right? You ready to try one by yourself? No? Let's try section 2 on our worksheet, part A, unless you have any questions on this one. Yeah, try part A. How are we feeling? Do you want to go through this, or should I give you more time? The answer's up here on the board.
I looked at the key and I don't understand where the number, like, how to set it up properly.
Okay. Let's go through it. Okay, so it says, so first of all, we have a balanced equation here. We have 3H2 plus N2 gives us 2NH3. Now, do you want to put the kilocalories in the equation or no?
Is it more expedient?
I like it better, but you really don't have to.
Why do you like it better? I mean, we saw the difference.
It just shows that what the ratio is 2 to whatever. But if you know that's what it is, it doesn't matter. It really doesn't. You want to just leave it out? No? Put it in? So this is this exothermic reaction or endothermic reaction? Exo. So what side of the reaction does it go on? Reactant or product side? Product side. So we're going to add 44.5 kilocalories. You guys know what a kilocalorie is? It's a food calorie. So when you look on the labels of your food, it says calories, but really it's capital C calorie, and that's a kilocalorie. Just, you don't have to know that, but okay. Good? All right, so it says how much energy is released. So we're looking for energy released. And that's in kilocalories, right? During the formation of 2.64 grams of NH3. So where do we start? We have a balanced equation, that part's done. So what's our next step? Start with what we know. We know we have 2.64 grams of NH3. Are we okay so far, Albert? Okay. And look at our mole roadmap. It says we go from grams to what? We always got to go to moles. That's the center of our map. We got to get there. So what's the molar mass of NH3? 17.3? 17.03?
Yeah.
Okay. Can we just say 17? Or do you want to say 17.03? It really doesn't matter, guys. 17 grams of NH3 to 1 mole of NH3. Are we good so far? Okay. And now what? Moles to what? Moles. We could go to moles to moles. Do we want to go to moles of a different substance? What are we looking for? Kilocalories.
Yeah.
So we're just going to convert moles to kilocalories. So how many moles of NH3 go on bottom? 2, because that's the coefficient in front of NH3, right? 2 moles of NH3 to what? How many kilocalories? 44.5 kilocalories. Moles of NH3 go away. We're left with kilocalories. That's what we're looking for. So we got that, and we should get 3.45 kilocalories of heat released. Since it asks for how much heat is released, then we just leave it as 3.45 kilocalories. If it asks for the enthalpy change or heat change, then yeah, we would write negative 3.45. Good?
I don't wanna go on some bunny trail, but like what, because we had kilocalories in here, it seemed like it was pretty, a lot more straightforward. What would have been the alternative
To what?
if you didn't have the kilocalories in that, in your equation? Like you said, oh, do you want me to
Oh,
put
okay.
kilocalories in there?
This is the best way to do it. Should we just do it this way?
I agree with you. I don't wanna go on some bunny trail, I was just curious.
So that's what I'm saying. Let's just do it. Just put it in. If you understand where to put it.
So where I struggled was just like, I didn't understand where the molar mass came from. Like,
Oh, okay.
why, like,
Why molar mass?
yeah, why there?
This right here.
Okay, so.
Going from grams to moles, it says use the molar mass for conversion.
Okay.
Are we good?
Yeah, that makes sense. Thank you.
Is that good, Kai, or do you want to go more?
No, I just wanna keep it as simple as possible. This is very simple.
It just depends. Do you know where to put this? And really, it really doesn't matter, guys. It really doesn't. I mean, this is just the way I look at it because this is where it's going. But, okay, good? All right. Do you want to try B together, or do you want to, because that one we start with heat or energy, and we want to go to how many grams of N2? It's just backwards. Do you want to try it together?
Do you just put the 155 on the left side anywhere, just you plus it, or do you have to write out the equation?
It's released, yeah. It's on the right side, not the left side.
Yes, thank you, never mind, that answered my question.
Because it's released, right? Yeah. Does anybody want to do this one together?
I would personally like to.
Okay. You want to do it together? Okay, let's do it. Yeah. You're here for you, so let's do it for you. No problem. Okay, so we have the same equation, but now we're starting with 155 kilocalories. Kilocalories of energy. And we got to convert this to grams of N2. This is what we're looking for. We know what we're looking for. We know what we have. So now let's just convert. And we're just going backwards. What can we convert kilocalories to? Moles, right? So we have 44.5 kilocalories. We put that on bottom so it can cancel the kilocalories on top. To how many moles of nitrogen? What's the coefficient in front of nitrogen? 1. You with me? 1 mole. If we're going to atoms, then yeah, there's 2 atoms in 1 molecule, right? But we're just going to the number of moles, and so we find the coefficient in front of our nitrogen. 1 mole of N2. So kilocalories goes away. We're at moles. We're not there yet. We got to go to grams. So now we go to grams. 1 mole of N2 has a mass of?
28.
Good. 28 grams of N2, because there's 2 nitrogens, right? And we do that, and we get something.
97.5.
Yeah, 97.5 grams of N2. Question?
With that negative on the 45.5 kilocalories, you don't ever use the negative in the equation unless it asks you for that specific.
Delta H.
Okay.
Yep.
I keep throwing it in there, but.
That's right.
Yeah.
So, and that's why I like to just put it in the equation, because then it's always positive. You don't have to worry about negatives. The only time you worry about negatives is if it says, what is the heat enthalpy? Okay. Or, yeah, I think, yeah. Good? And you also know if it's written out in the equation for you, if it's on the right side, it's going to be negative delta H. If it's on the left side, it's on the reactant side, it's going to be positive delta H, right? Any questions with enthalpy? Good? All right, let's move on. To entropy. Anybody know what entropy is? It's the measure of disorder in a system. Measure of disorder. So, because it's a measure of disorder, not order, it kind of throws us off a little bit as far as thinking, okay? Now, the word disorder has an S in it. So we're going to call entropy delta S. Are we good? If we have a positive delta S, a positive delta S refers to more disorder or increasing disorder. So disorder is negative word, right? Dis. So naturally we think that's a negative, yeah? But remember, entropy is the measure of disorder. There's more disorder, that means it's positive. Good? If we have a negative delta S, that's decreasing disorder. Going down, that's why it's negative. Does that make sense? Increasing is positive, decreasing is negative. So it's kind of like when you're at home and your neighbor, they move out, right? So what happens to their property? Goes to pot, right? It just goes downhill real fast, doesn't it? You ever notice that? People don't put love and tenderness in their house. It just goes downhill, okay? Without putting energy into it, things tend to go toward disorder. What's that?
Isn't that one of the laws we learned about in biology? Like the universe wants it always increases
In disorder?
entropy always increases
Yeah.
without energy.
Not always, but without input in energy, it does. Okay, if you input energy, it will not go into disorder. Does that make sense? That satisfy you, Andrew? Okay. All right, so let's start simple again. We have H2O as a solid going to H2O as a liquid. Is that increasing in disorder or decreasing in disorder? That positive delta H or negative delta H? Or sorry, delta S. Let's think about it in terms of when first of the semester, I kind of drew a picture of solids versus liquids versus gases, right? So a solid looks something like this. Remember this? It's all structured. And a gas is a little bit more spread out and it can flow. Which one is more disordered? Liquid is more disordered. So this is a positive delta S or negative delta S? Positive delta S. Are we good? So it goes toward more disorder. And if we flip-flop this around, it goes toward less disorder or more order. Good? Let's try something a little bit more complex. C8H18, and I'll balance this for you, plus 25O2 gives us 16CO2 plus 18H2O. So this is gasoline burning in oxygen, and it produces carbon dioxide and water. So your first thought, does this go to more disorder or order? You guys ever burn gas? What does it go in? Does it go to increasing disorder or decreasing disorder? Increasing disorder. It goes wild, right? You put a little spark on a hayfield, and it just grows real fast, right? Same thing with gas. Just you give it a little teeny spark, and all of a sudden, it's all gone, right? Or if it's a propane, even more, right? Because it's a gas rather than a liquid. Good. But it's still pretty. So we can kind of tell in the situation. But what if I don't know what this crap is? I don't know, what is it, right? How many times do we know all of the equations we deal with in this class? No, we have no idea what it's talking about, right? You probably wouldn't have knew this if I didn't tell you this is gas, right? So how do you tell if it goes toward more order or disorder? Just by looking at the equation, because that's really going to be most useful, right?
Is it like oxidation and reaction?
No, easier. If you can balance equations. Well, this one's already balanced. We start with how many particles on the reactant side? 27. And we go to how many particles on the product side? 34. We have a little bit of particles, and we go to more particles. Does that make it more order or more disorder? More disorder. Does that make sense? So that's the easiest way to look at it. Well, in my mind. What about you guys? Feeling okay with that? Or do you have a question? So if we get more particles, that goes to more disorder. So this is a negative delta A, a positive delta S, right? See, even there, I just made a mistake. You have to think about it every time. Positive means more disorder. Good? All right, let's take a look at section 3. There's 4 reactions there. Which one do you want to do together? The bottom right one? Well, that one looks icky, right? So we got C3H5N3O9 plus, it doesn't plus, breaks down into water plus carbon dioxide plus nitrogen plus oxygen. Okay, what's our first step? We got to determine if this is increasing disorder or decreasing disorder. Balanced equation. Yeah, that's just, so this one's kind of a bear. But should we show our work? Okay. So we have CH, N, and O. CH, N, and O. All right, where should we start? We should start with this big, huge compound, right? Which element should we start with? What?
Oxygen?
We could start with oxygen, but there's 3 places on this side. It's like, that's gonna cause a havoc, probably. Not 100%, but most likely it will. So let's start with either hydrogen, nitrogen, or carbon. Should do hydrogen, there's 5, right? 5 here, 2 there. So what? One's odd, one's even. What do? Least common multiple. What's the least common multiple of 2 and 5? 10. So we better put a 2 right here and a 5 right here. Is that right? You following? So hydrogen has 10 on each side now. That one's good. Now let's just do carbon. How many carbons do we have on the left side? 6. So what coefficient goes on the right? On the left side of carbon dioxide? A 6, right? Carbon and hydrogen's good. Now let's do nitrogen. How many do we have on the left? Also 6, right? Good. And so what do we need to put in front of N2? A 3. So we got 6 there. Okay, so far so good. How many oxygens do we have on the left? 18, right? How many do we have right here for water? 5. How many do we have here for carbon dioxide? 6, almost. 12, right? 6 multiplied 2. We good? And then something times 2. We already have how many? 17. We just need one more. So what's that coefficient of oxygen? 1/2. Can we leave it like that? We can't leave it like that. We can balance. It's balanced now. So we have 18 on both sides.
We have to multiply by 2.
We have to multiply everything by 2. So that's going to be a 4 here, a 10 here, a 12 here, 6 here, and a 1 here. Good? So how many particles do we have on the left side? Just 4. And we have a whole lot on the right side. So what is this? Negative or positive delta S? Does it go toward more increasing disorder or decreasing disorder? Increasing, so it's positive delta S. Are we good? Now, can we see that that's going to be that way just by looking at it without balancing? You can kind of see, right? There's one versus 4 products, right? 1 reactant versus 4 products. So, yeah, and this 1 has a lot of big numbers, so you probably didn't even have to balance it. Yeah.
I just wanna ask about the last one. You said that, because, the last one we did, it broke down into CO2 and H2O, right, the gasoline one.
This one right here?
Yeah.
Okay.
You said, we should be able to see that it'll break down, or that it would be more chaotic, or more positive delta S, based off of the compounds, or the.
On this one, there's 2 and 2, so we better balance this, right?
Does it make sense to look at it like, okay, the products themselves are the gas and the liquid?
This is also a gas,
Okay,
right?
because it's steam. But like,
This could be a
thought
gas
it
and
was
this is a
gases
gas, right?
gases.
Maybe it's all gaseous.
Oh, okay.
And
So if there isn't that
I-
fire there, that's not safe.
the only way we can do that is if it's a physical change.
Okay.
Okay, when it's going from a solid to a liquid to a gas. Otherwise, I would balance this. Great question. Does that make sense? Yeah,
The question to the left of it, the H2, N2,
Uh-huh.
and H3, could you, since it's two products to one, kind of similar to this, is that too soon to predict that that's gonna be decreasing, just from looking at it?
That's,
Good,
that's
great,
what I was asking, but put words.
Yeah.
So thank you.
Yeah, you're
great,
welcome.
great question.
Gas to liquid,
Um,
liquid being more structured than gas.
It's a chemical change, so it's not a physical change. It's not just going from gas to liquid. You're not just cooling it, right? I would balance it every time.
Okay.
I would, just to make sure we got it,
Yeah.
right? I can't say if that's always gonna be the case.
Okay.
I can't.
Like, I don't wanna have that
Yeah.
big bad habit.
So,
if it's not-
yeah, I would just always balance it, 'cause especially on something that simple, it's not gonna be too hard to balance, right?
Okay.
You guys practicing the other ones? Or are we done? You ready for some answers? Or not yet? Not yet? Okay.
I counted up the carbons, hydrogens, oxygens. And again, over here, I'm like, okay, so I got,
You said you have 3 oxygens.
all right, 3 here.
Mm-mm. There's the 5 right there. This is saying we have 5 waters, and every one water has 1 oxygen. That means we have 5 oxygens.
Okay.
So 5 oxygens, 2 oxygens, that's 7 there.
Try to,
If, yeah. Does that make sense?
Yep. Yep.
And then over
because it's
here,
bonded to that.
over here we have 1 plus what times 2?
1 times 2, right?
Well, if we have 1
Mm-hmm.
plus what number times 2? 1 plus what number times 2 is equal to 7? Write it out. 1 plus what number times 2 is equal to 7?
6.
Subtracts 1 to both sides. Right? Does this make sense, or do you hate that?
It's a different way. I know it's algebra.
Okay. So we got 2x is equal to 6.
So that's 3.
So x has to be 3, so we got to put a 3 there. Now let's just check. 3 times 2 is 6, plus 1 is 7.
Okay.
Do you get that?
Yeah, yeah. That's why I don't have it there. Not here. So I need to place it.
Place what?
So what I was missing was 3 to get us to 7 because we added 1.
Yes, so you just counted this side
Wrong.
off.
Okay.
Yeah, Sandy.
I got stuck.
Okay, so first letter is always capitalized.
Oh,
So just make sure you do that,
okay.
okay? Otherwise it looks like milligrams and it's not.
Okay, yeah.
All right. So, how we coming? Do we want to do any of these? Or, okay. So, we come over here, and the best place to start is here.
Okay.
And maybe you did that. So I have 4 on this side, so you put a 2 here, that makes 4.
Mhm.
Good. So we have 2 times 3, that's 6. So yeah, we better put a 6 right there.
Okay.
And that's it.
And
You
then
did it.
I didn't know what to do after that.
Okay. So now you count. We have 6 on this, 6 here, and 1 here. That's a total of 7 on this side.
Oh.
And over here you
okay.
just have 2. So we're going from disorder to less disorder.
Uh-huh.
Does that make sense?
So that's gonna be negative.
Negative delta S. Uh-huh.
Okay, yeah.
Make sense?
Mm-hmm.
Okay, are we ready to move on? The answers are right up here in order. Do we have any questions? All right, let's move on to the last topic for tonight. Are you guys feeling okay? All right. So the next part is free energy, or Gibbs free energy. And yeah, Gibbs with a G. Uh-huh. And what this is, it tells us whether or not a reaction is spontaneous or not. Do you guys understand the word spontaneous? Because we use a word spontaneous that means different than what it means in chemistry. So spontaneous is just spontaneously did something, right? We just, yeah, let's just go do this, right? It's kind of the same meaning, but not really, okay? So spontaneous means something is, so in order to get a chemical reaction to happen, you have to give it energy. You have to. You cannot make it react without not giving it energy. Does that make sense? But just like the gasoline, what did we do to get it started? Give it a little teeny spark and it's gone, right? So if we give it a little teeny spark and then don't give it any more, is it going to continue to go by itself? We call that spontaneous. You with me? Okay. So Gibbs free energy, since it's a G, we're going to say delta G. And also there's a G in energy. So that's delta G. So this is the measure of spontaneity. Or of amount of, measure of the amount, I don't know if it's the amount, I'll just say measure of spontaneity. Is that a good word? Is that a word? Okay. So we have negative delta G and positive delta G. Negative delta G is when it is spontaneous. And positive delta G when it's not spontaneous or non-spontaneous. So let's think about this for a bit. If it's spontaneous like gasoline, it just goes wild, right? And what about, is burning gasoline exothermic or endothermic? Exothermic. And exothermic is negative, delta H. Another name for spontaneous reaction is exergonic. And another word for non-spontaneous is endergonic. So you can kind of relate that with exothermic versus endothermic, right? Exothermic is negative, endothermic is positive. Even though it's the measure of spontaneity, then it kind of goes opposite of what entropy does, right? I hate that for you. But so why is it this way? Because somebody described it that way and it stuck. So maybe it should have been described differently. I don't know. But that's what it is. Okay. So let's do some examples on our worksheet. So this is really the last part of the worksheet that I want to. I'm not going to do section 5 of the worksheet. You can just cross that out. I mean, if you want to do it, you can, but we're going to keep it simple here. So dissolving sugar in water. If you have a thing of sugar and a big thing of water, is it going to dissolve by itself without you doing anything? No, so we got to give it a little bit of energy and pour it in, right? Do we have to keep stirring it to get it to dissolve? We don't. Yeah, it dissolves faster if you do, right? But if we pour it in, it's going to dissolve by itself. So once we initiate it, that's all we have to do. We can step back, and if it's cold water, we might have to wait a long time, but it's going to dissolve, right? Okay, so that's considered spontaneous or non-spontaneous? Spontaneous. You always have to give it a little bit of energy. It's just like that spark in the gas, right? So this is a positive or negative delta G? Negative delta G. Are we good? Sugar in water, H2O, is negative delta G. Okay, what about automobile gasoline evaporating on a hot day? So it starts evaporating. Do you have to continue to give it heat to keep it evaporating? Yeah, you do. So if you spilled some gas at the end of the day, and it was a little warm, so it starts evaporating, right? And then cools off. Let's say we're living in the desert. Hey, we are living in the desert. And it gets cold at night, right? Is it going to continue to evaporate? Maybe not, right? So this is non-spontaneous or positive delta H.
Because you'd have to continuously give it energy for it to work versus the sugar when you just give it.
That's
all
right.
and it
Mm-hmm.
just-
So positive delta H, because you have to continue to give it the heat from the hot day. If you turn off the sun, it's not gonna evaporate anymore. Good? What about burning propane gas? Spontaneous, negative delta G, right? So burning propane C3H8, that is negative delta G.
Are you saying that because you initially give it the spark?
Yeah,
like at night?
you give it a spark and then it's gone, right? And charging a cell phone battery. Spontaneous? Non-spontaneous. Because if you plug it in and say, okay, I gotta go, you unplug it, is it gonna keep charging? No, you gotta keep giving it energy, right? So charging is positive delta G. Make sense? All right. Now that's great, but that's not really chemical reactions except for one of them, right? So we're not going to get into the deep stuff because you say, okay, what about iron with oxygen and it rusts at a 30 degrees Celsius temperature? Is that going to be spontaneous or non-spontaneous? Now there's an equation that we can use to guide our thinking, but I want to use this equation for simple cases only. Are we good? So this equation is given to you on your reference sheet, and it is delta G equals delta H minus the temperature times delta S. And this temperature must be measured in Kelvin. You guys remember how to convert Celsius to Kelvin? It's also on our reference sheet. Okay? And the reason it has to be Kelvin is because if we have a negative temperature, well, that'll change everything. And Kelvin doesn't get negative. Are we good? All right, so let's make a little table here. So we got delta H, delta S, and delta G. And we can use this equation to guide our thinking. If delta H is positive and delta S is negative, so if they're different, let's plug numbers in here. If this is a positive number, delta H is positive, and delta S is negative, well, temperature is always going to be positive, right? So what's a positive minus a negative? What's a positive number? Subtract a negative number. Subtract a negative turns to positive, right? And if you can't do this in your mind, use a calculator. Pick some positive number, subtract some negative number, and it's always going to be positive. Are we good? Does that make sense or no? Should I pick some numbers and show you? Here we go. Let's pick a 2. That's a positive number. Then let's pick a negative 3. So H is 2 and S is negative 3. And let's say T is 1 for crying out loud. Something, right? It's still going to be a positive number, so it doesn't really matter. So we have 2 minus 1 times negative 3 is a negative 3. 2 minus a negative 3 is equal to 5. And you can plug this in your calculator, and it would show you the answer. Okay? Are we good? If delta H is negative and delta S is positive, so we have a negative number over here, positive number over here, but we have what's a negative number minus a positive number? It's negative. Make sense? But let me show you something. Remember I says delta H and delta G are the same? XO and XO. If they're opposite, if delta H and delta S are opposites, then delta G is the same as delta H. You can remember it that way, or you can use this equation to guide your thinking. If you're good with algebra and math, then that might be the easiest method. If you hate it, well, you might want to stick with this one. And I could teach you more on that. It gets a little icky, and I'm not going to test you on it anyway. How's that? Should we just leave it there? Okay. And the reason I do that, I don't like to just not teach you stuff, guys, but the reason I do that, if you look at this worksheet on this table, does anybody know if when iron rusts at a 30 degrees Celsius day, if that's exothermic or endothermic? Do you know? Yeah. Who knows, right? Yeah. We probably don't have the experience for all of these little things. Now, if it was something like liquid water going to ice, yeah, we all know that. We have experience with that. But there's going to be a lot of these, it's like, we don't just know that. So I'm going to throw that part out. Are we good? Unless you want me to spend a lot of time giving you experience. I can't do that, okay. So I hope you're okay with that. Okay, ladies and gents, that's it for tonight. Thank you and drive safe. Okay, we have one more time next time before we take the test or the exam.